Okay. Um, in this tutorial, we're going to be doing a point mass with translational motion. Uh, the the main things that we're going to cover is Earth's gravity, which we have to choose a model for our gravity. The Coriolis force and the centrifugal force. These two show up because we're going to be working in a non-inertial reference frame, which is the Earth rotating reference frame. And depending on how long this takes, I may or may not do air resistance at the end. So the first thing to decide is, what is our coordinate frame going to be? And since we're not going to be doing, like space related kinetic vehicles, rather it's just going to be something, like maybe like a short range missile of sorts. Uh, it's best to not have to bother with, Newton's laws or Einstein's relativity. So instead, we're going to be using a very simple coordinate system, which is, somewhere on the surface of the ellipsoid Earth that we live on. We will have a, let's see here, we will have an angle from the equator or an angle from here, which would be the latitude line. And then from there, we will define our coordinate axes here, where we will define z as going, perfectly up from there. We'll have, I believe it's y going this way, and then, following a right-handed rule, x would be going into the page. So in this specific coordinate frame system, we would have, whoops, let me do this properly. X hat would be in the east direction. We would have y hat as north, and we would have z hat as the straight up from, our origin. And so you can see that there's going to be, two main transformations that have to be made. One which starts at the Earth's origin and goes to the location of interest, and then another, like, position vector which goes to like where our vehicle actually is. Yeah. And so, from there we'll choose our gravity model accordingly. We'll calculate the values or the expressions for the Coriolis and centrifugal forces. And yeah. So yeah, that is the goal for now. I just to clarify something, I know I said I was going to do this in spherical coordinates, but then I realized that that's going to be very difficult, and odds are I'm not going to be trying to design things that go into space. That's a little out of my budget, you could say. And so, something that stays within, the Earth's atmosphere is perfectly fine for this specific project, and that's what I will stick with. As a result, there's going to be a polar coordinate system going around here, and then a Cartesian one here. And since, nothing I make will, be shooting, thousands of kilometers, the curvature of the Earth is virtually non-existent. So yeah, that is the justification for why we will be using the models that we do. So yeah, going from there, let's jump right into it. So first thing that comes up is the Earth's gravity model. So there's no easy way of saying this. I went to Wikipedia, searched up theoretical gravity, and this is the thing I found. Now, to go a little bit more into detail on this, so what this model does is it gives you the value of gravity depending on your location on the Earth. So, this is something I'd like to explain just in case people are unaware. But the Earth is not actually a perfect sphere. Since it's spinning in the center, there tends to be like a little bulge around the equator, right? So this would be like the axis where it spins about, right? And because of that, we have a semi-major axis and a semi-minor axis. And this length is not the same as this length. And as a result, your value of gravity actually changes as you vary the angle from, the equator to the poles. Sorry, that didn't reverse. From the poles to the equator and back. And so that is what this equation here models essentially. Is, we start with the gravitational constant at the equator, and then we measure the value of gravity as we change our phi angle, as our polar angle changes. And so obviously, we can see here that when when phi is 0, this entire term will be 1 over 1, and so we have the gravity at the equator, right? So I guess the more accurate picture here would be it measures this angle. And obviously, like, there's a bit of symmetry here, so it's the same thing going up and down. And this is the equation that we're going to be implementing. Keep in mind, this is only for the phi dependence, right? This is only for the surface of the Earth. If we go down a little further, we can see that there's another system for height dependence right here, Cassini's. And as you can see, you simply take the model for the phi dependence and add in an extra term to account for, the change that occurs as you go up and down. We can actually even see here that it says that this adjustment is right for aviation purposes, which is what we're doing, and will only, fail when we're trying to go into outer space, 100 kilometers or more. As I just mentioned earlier, we're going to be using ballistics stuff, so we should be staying in the atmosphere for the vast majority of everything we do. And if we were to go into, if we were to try to extend this tool to, deal with space, we would simply have to update our gravity model. But we're not going to do that now. So yeah. So we will start by implementing this as our gravity model. So let's go into MATLAB, and we'll build off the same thing. I'm going to move this off to the side just so I have a full screen here. Yeah, and we're just going to add it in as we normally would. So in our physics functions, we'll create a new script, and we'll call this Earth Gravity. And let me just pull up the one I made earlier today because I made a lot of mistakes while doing this. So we have our function. We want to get out the value for we want to get the vector for gravity out, which we expect it to be straight down, then that is what it's going to be. But for the sake of consistency, we'll output all three values. This will be a function of latitude, altitude, and the mass of the thing we care about. And this is just so this right here is just a little naming convention I do, so it makes my life easier when I go back and try and edit these things to look for errors. But there's really no need to do this if you don't feel like it. So latitude, I want to know immediately that it's in degrees, right? Latitude is normally measured in degrees. And then force of gravity, I'll just add one more line here. We're going to have Fg is equal to a vector Fgx, Fgy, and Fgz. Yeah. And so let's go through our things one by one. So first we have our constants. Pretty straight. We're going to copy them straight from the what's it called? From the site that we had earlier, right? They give us the value for the equator right here. They give us the value for the poles right here. They give us the semi-major and semi-minor axes, and then everything else is just obey these equations and plug and chug in here. Also, we have to keep in mind that phi is measured from latitude, right? We're starting at the equator. Phi is 0. This will be 1, and so we want to make sure that we don't make any errors with that. And we also want to remember that everything is measured in. We want to make sure we don't make mistakes between radians and degrees. I personally like radians, so I'll be converting everything into radians. These are the two variables that I'll be using everywhere, phi and h. Whoops, I guess these aren't really constants; they're more conversions. Going into the constants, it shouldn't be nothing too crazy yet, right? We have gravity at the equator. Oops, gravity at the equator, which 9.780326777. You might be wondering why that crazy amount of precision. I don't know. I just felt like it. You can use more or less depending on your application. And both of these values are the values copied from the Wikipedia page. Going on, we also have to do the semi-major and semi-minor axes. So for the semi-major, we have 6.378137 meters. And for the semi-minor axis, we have 6.6356 752 meters. And then we need to just calculate like a constant k, which is going to be b times gravity at the poles minus a times gravity at the equator, altogether divided by a times gravity at the equator. I'll just add a space here so it doesn't look a little ugly. And maybe a bit more space so I have room to work with. Okay. And then we also have to calculate the e squared value. So in this equation, they only use e squared. So there's no need to, do the square root and then square it again. We'll just calculate e squared directly. And e squared is going to be a squared minus b squared altogether divided by a squared. This should look familiar for anyone who remembers their pre-calc. One other thing I like to do is make parentheses around the denominator just because I've made errors in the past and I don't want to make them again. So there we have the constants. So we will calculate the Somigliana gravity. I'm sorry if I'm saying that wrong. And this value, we're just going to go straight from the equation. So we're going to call it G naught, and it's going to be equal to GE times 1 plus k times the sine of phi squared. And I'll actually put this in parentheses just to make sure I don't make any silly mistakes. Squared, and is going to be divided by the square root of 1 minus e squared times, and this is in parentheses again, sine phi squared. And we can see that we have all our parentheses, no errors, so that's good. And yeah, so there we have the this expression right here. As for the other one, where did it go? There it is. We can see that we just have to add in a few constants, right? K1 through 3, and then we'll follow this equation right here because it's the simplest one, right? No weird terms, no room for error. And so let's do that. We have to define 3 more constants, right? K1, K2, and K3. And K1 is going to be equal to 3.15704 e to the e negative 7, which is just 10 to the times 10 to the negative 7th. Second constant is going to be 2.10269 e to the negative 9th. And the last constant is 7.37452 e to the negative 14th. As you can see, these terms are very small, but they could very well become relevant if we if our artillery was going high enough. Yeah. So from there, let's just calculate Cassini's gravity. So following the equation that was shown earlier, we have f of g is equal to, and just something I'd like to mention, this particular model for gravity goes in the straight down direction. It's only accounting for the mass distribution of the Earth, or rather, that's what I'll be assuming. So to do this, we just do mass times gravity, which is g naught, and then this is just Cassini's thing right here. So we'll do 1 minus, in parentheses, k1 minus k2 times sine phi, and then sine phi is squared, so I'll put this whole thing in parentheses. Sine phi squared, n parentheses, times h plus k3 times h squared. And this should be copied exactly, so no errors, no errors. So yeah, and there we have the gravity model that we'll be using. This is the final gravity vector due to the Earth's mass that will be coming out. Alright, so we have that. The next thing that we're going to look into is the, let's see here, is going to be the Coriolis Force. So the Coriolis Force is due to, or is one of 2 fictitious forces when we have, a rotating reference frame. So it's to get the specific details on how this is all derived, you would need to go into like a classical mechanics book maybe, and go into a section that's likely titled non-rotating reference frames. Personally, I would recommend Classical Mechanics by John D. Taylor, 4th edition. That's the one we're using in class, and it's pretty good in my opinion. But to explain the Coriolis force in the simplest of terms, the way it works is you have your reference frame. Oops, let me just give myself a little more space and open up and get my reference image up so I don't make any mistakes here. So sorry for the delay. I just need a moment to grab my thing. Okay, so yeah, looking at the Earth from above, what we have is, we have the Earth, which is spinning using the right-hand rule, it's spinning this way, right? This is the way the Earth spins. And so the vector for this is coming straight out of the page. And the formula for the Coriolis effect is F vector Coriolis is equal to 2 times mass times the velocity crossed with the rotation vector. And so to give like a quick summary of how this works, what it means is wherever you have your velocity vector, let's say our particle's moving this way, the Coriolis force is simply the cross product of this vector with this vector. And so you can imagine, if you like hold your right hand out in this direction, and then you curl your fingers up, you'll see that your thumb points this way. And so the force itself would be going this way. And the same would be true, like, let's say we have like a vector this way. We do the same thing, it would point this way, right? Yeah, just made sure with myself, but yeah. And so this is the equation that, that governs how this works. One thing that we do have to keep in mind, is that the velocity vector is actually going to be a state vector, meaning it's going to be an input to, our system. It's going to be one of the variables that we actually solve for, right? If you remember reduction of order, we're going to be solving for that variable. So yeah, from there, let's just implement it and make another script. We're going to call this Earth Coriolis, and let's just do this function fcor is equal to Earth Coriolis, and then the inputs are going to be some velocity vector, some latitude, and some mass, right? And the latitude will matter simply because the latitude determines, what this spinning is, right? If you're further away, it will have a much less impact. It'll have a much greater impact because omega would be larger, right? If you can imagine when you're at the poles, I'll use omega as rotation of the Earth, right? If you're at the pole, there is no Coriolis force because no matter which way you're moving, a cross product like this, at this exact point, it'd be undefined more or less, right? And so because we defined our coordinate system as we did here, we care about, the angle that it's going to make, right? We translate this vector over, right? And then that's going to determine, what the effect is in the z direction and the y direction, which is why we need to know the latitude, right? Because we can draw a similar triangle here. I'll use the same color right there. So implementing this in, we shouldn't have too much issue. Let's do this. So Earth Coriolis. Oops. Coriolis. Hope I didn't close anything. Okay, I didn't. So yeah. So first we have our velocity vector. This is just going to be v is equal to vx, vy, vz. We have the Coriolis force, and this is going to be F core is equal to F core x, F core y, F core z. And obviously the same conversions as before, where we do phi is equal to the latitude. This time we're going to do plus 90, right? because we're measuring not from the bottom up, we're measuring from top down, right? So the latitude is this value right here. We care about this value, right? Obviously, it's easier to do, just to use a trig identity, but I want to use this value simply because it shows up right there. And I'd rather do this than, 90 minus it. So implementing this in, we have latitude plus 90 gives us the actual value. Pi over 180 gives us radians. Next up, we have our constants. So we have our omega, which is the rotation of the Earth. 2 pi divided by 24 times 3600. So all this says is that we do 2 pi radians, right? One full rotation in 24 times 3600 seconds, right? And so this is radians per second. And also we want to make sure we get the value right, which is, in the coordinate frame that we've defined here, this x and y frame. Here I'll draw another image. And actually, I'll erase this one. This is not very relevant. Yeah, so we have our first position vector here, right? So this right here is our latitude line. Oops, I'll just go latitude. We have our omega vector right here, which is going to fall this way by a value of theta. I'm going to use different colors just so I don't confuse myself. Yeah, we have our theta value right here, which we got from the other thing. We defined the z vector as going straight up. I'm going to make this a little bigger. Our z vector is going straight out. We have our y vector defining north, and then we have our x vector going into the page, but I'll draw it just like this, symbolizing it's going into the page. When we translate this vector over into this frame, right, what we find is that this is the theta vector, and this vector will have its components in the frame that we care about. More colors, right? And so the component in the y direction is going to be the sine theta, and the component in the z is going to be this, and the component in the x is this. So x hat will have none of the thing, y hat will have a little bit, we'll have the sine, and z hat will have a cosine factor from this omega, right? This is the way we've defined up. So yeah, from here, let's just add that in here. So x component will be 0, y component will be sine of phi, and the z component will be cosine of phi. And this makes sense from the image we just drew. Finally, we have to just calculate the Coriolis force. Coriolis force, yeah. And this is just a standard cross product. Actually, I'm going to use this opportunity to define the cross product because we haven't done that here. We could use the default one in MATLAB, but it's better to be defining things on our own. So let's go into math functions, new script, and we're going to call this Cartesian cross product. Yeah. I know there's more efficient ways of making of making a cross product. I'm just going to make my own here for now, just because I feel cool when I do. Cartesian cross product. So C1 and C2 are the two vectors that we care about. So actually no, not C1, C2. What am I doing? Let's call this X1. Or no. You know what? No, C1, C2. This is the way I did it earlier, and I made no mistakes. So yeah. So the way we have it is we defined X1 as C1, 1, Y1 as C1, 2, and Z1 as C1, 3. And then we just define all of these one more time, but this is our second vector now. So 2, 2, 2, 2, 2, 2. Yeah. And I'll just shove in parentheses. I'm going to skip the derivation for this. This is just cross product is equal to, and I want this to be a row vector. I want this to be a single row with 3 columns. Or yeah, something like that. So let's just do this. Y1 times Z2 minus Y2 times Z1 dot dot dot. This one's going to be Z1 times X2 minus Z2 times X1 dot dot dot. And the last one's going to be X1 times Y2 minus X2 times Y1 dot dot dot. So yeah, these are the values. We can just save on a bit of time in that, you know, we can just move this here, put that there. Let's do this. Y1 shows up right here and right here, and Z1 shows up right there and right there. And then we just repeat them for the x value. So x2 shows up here and here. Y2 shows up here and here. And Z2 shows up right here and right here. If that was confusing, pause and rewatch it, because I did that in a weird way. So it might help to go through it one by one. Yeah. No, not minus. Okay, there we go. And that's the standard, you know, Cartesian cross product. Oh, another reason why I didn't do spherical coordinates is because I don't want to do cross products in Cartesian. They're very annoying, I assure you. Believe it or not, if, like right now, if you go to like Wikipedia or Google and search it up, like you'll get a bunch of weird results. And if you try to recreate them, you'll realize it's annoyingly difficult to get everything to agree. Anyways, now that that's done, we can add in our Coriolis force. So F core is going to be equal to 2 times m times the Cartesian cross product between v and omega. Right? This follows from, you know, this formula right here, which you can find in any standard classical mechanics book. So yeah, this will give us F core, and we have our Coriolis force. Let me go back to physics functions. All right, so we have our Coriolis force done. The last one last fictitious force that we need to account for is the centrifugal force. To the comment section that might try and, if I'm popular one day and the comment section says, you know, centrifugal force doesn't exist, I'm here to tell you it does. It's just you have to be in a non-inertial reference frame for it to exist. And normally, if you're smart, you don't do that, but sometimes you have to. And this is one of those cases here. So we have force centrifugal, and this is going to be equal to Earth centrifugal. And the inputs are going to be the position vector from the origin, right? So there's two position vectors that we care about. We care about the position vector from the center of the Earth to our origin, which is, you know, the starting point of where we do stuff. And then from there, there's another vector that would go out to where the vehicle is actually located in that reference frame. And so we care about both of them here. We also care about latitude, and we also care about mass. So yeah, the formula for the centrifugal force is a lot more straightforward. Well, as straightforward as you can be. But start drawing here. So for the centrifugal force, the formula is mass cross r, and then we cross this with the omega vector again. So I would highly recommend going into a classical mechanics book if you're, you know, actually curious on how this works. But the way I like to think about it is, you have your origin, you have your axis of rotation here, and then your position vector goes somewhere like this, right? This is your r vector, and this will trace out a circle in this frame. And the centrifugal force is purely dependent on this value right here, on this distance right here, right? You can imagine the centrifugal force only, like, flings things outwards, which means it doesn't really care how high up you are. So it only cares about this vector right here, and this vector we'll define as rho. And this is, if you know a bit of multivariable calculus, you'll know that this vector right here, that rho, is in fact this quantity right here. And then when you find the cross product, that gives you the outward throw, you could say, and it also gives you the direction. Wait, no, I misspoke. This is rho. What this gives you is your tangential velocity. Yeah, and then when you cross a rho with this, sorry, yeah, when you do v cross rho here, that'll give you your centrifugal force, which is going to be in this direction. Oops. That explanation was probably not very good, but like I said, go to a classical mechanics book. They do it way better than I do. That's just the way it is. But I will say this: the simplification for this does turn out to be something along the lines of m omega squared rho vector. Normally you'll see this written as rho, like the magnitude of rho times rho hat, but I'll just use rho vector because we can calculate that fairly quickly. So to implement this into our thing directly, let's see, centrifugal, yep. So yeah, let's do that. So Earth centrifugal, whoops, come on, there we go. So first we have our position vector, which is going to be r is equal to, it's just going to be x, y, and z. We have the centrifugal force, which we know will not act in the x direction, right? So if you can see from this image, right, when we define our coordinate system here, assuming, like, this is like the surface of the Earth, our z vector will go this way, our x vector will go this way, oops. Our y vector, our y hat will go that way, and our z hat will go in this direction. And there's no component of this in that direction. This will fall purely into these two values. So let's just do that. So we have f centrifugal, and this is going to be 0, f sen y, f sen z. I did not do that here, but I will make that right here. So these two will also be 0, right? And the Coriolis force, a very similar thing comes up in here, right? Because this term is 0, one of these will be 0, but I didn't calculate which one. So yeah, let's just do this. Conversions, constants, and then centrifugal force. Oops. Centrifugal force. So the first conversion we make is that we get phi, and this will be the latitude times phi divided by 180. This is the latitude in radians. We also want the polar angle, which starts at the North Pole and sees how far down you are. And this is going to be phi plus pi over 2. You can draw a quick diagram and convince yourself that that's the case. Then we have omega is equal to 2 times pi divided by 24 times 3600. We also have our semi-major and semi-minor axis. So the reason why these two matter now is because when we're at either of the, because our Earth, we're no longer assuming that it's a perfect sphere. We're assuming it's an ellipsoid of sorts. So because of that, our values are not going to be, we can't assume we're on a perfect sphere. We're going to assume that we have an ellipsoid Earth, and these are the values from before. We also have to care about our Earth, which is the position vector from the center of the Earth to our origin. And we're going to assume that our origin lies somewhere on the surface of the Earth with no deviations from now. We're going to assume it's an ellipsoid. And this is going to be cosine phi b times sine phi. This just comes from an ellipsoid in 2D, and there's no impact on the x, right? Um, yeah. So once we have that, we can just look at our row vector, which is, the vector from, so the row vector goes from, is going to be like our quote unquote final vector. There's going to be the vector that, we start at the surface of the Earth, and we're going to add the value, for the, what's it called? For where our vehicle actually is. So it's going to be r plus r Earth times sine theta. Yeah, oops, I forgot to add a semicolon here. If you're wondering why this is 0, a quick thing you can do to convince yourself that it doesn't matter is that it doesn't matter where the Earth is or which longitude line you're on, right? If we assume, because there's a bit of symmetry here that we're exploiting, right? We have our ellipsoid of an Earth. It really doesn't matter where along this line we are, right? Because there's a symmetry about it. There's no symmetry about this anymore, right? Normally, if the Earth was a sphere, we'd have spherical symmetry. Here, we only have a symmetry about this axis. And what that means is that we can assume we're anywhere on this latitude line, and it won't make a difference. And since we're not accounting for things like day, night, and whatever, we don't need to account for, that specific part of the thing. So finally, we have to calculate the centrifugal force. So force centrifugal is equal to m times omega squared times rho, right? And rho is just the the magnitude of rho times rho hat. This goes right here. Yeah. The odds of me making a mistake in here are pretty high. So if you catch any mistakes, do put them in the comments so I can fix this. I am doing this in a bit of a rush, so yeah. All right. So we have our three forces that we care about, right? Gravity, Coriolis force, centrifugal force. Now we just need to shove them together into one gigantic, equations of motion. So let's do that. Call this, and we'll call this gravity EOM. Yeah, and so this is going to be a function which will return a dx, and it's gravity EOM, and it's going to take in, per the standard we defined in the last video, a, what's it called? Time, state vector, mass, and latitude, because that's an input now. And, alright, so let's just define some stuff here. So we have our gravity EOM, let's do a few of these. So obviously we have our state vector, which is x. The first three of these are going to be our Cartesian coordinates, right? X, y, and z in our own coordinate frame. Next up we have 4 to 6, which, as I mentioned last time, they're going to be our derivatives, y prime, z prime. And then finally we're going to have latitude, which is going to be defined in degrees. So yeah, now we just have to put in our three models for our three forces. So we have Fg, which will go right there. We have our Coriolis force, which we will put in right here. And we have our centrifugal force, which is going to go right here. Paste, and get rid of these. Boom. Okay. Now we just need to make a bit of substitution. So altitude is, how high above the ground we are. We've defined that to be our z coordinate. Z is the third variable in our state vector. We also have to input the velocity, which is the last three components, so 4 through 6. And then finally we have to put in a position vector here, which is just going to be 1 to 3. And as you can see, it all works out quite nicely. So finally we just have to do the sum of these things. So force gravity, force Coriolis, plus force Coriolis, plus force centrifugal. And then we just have to define our dx vector. So dx 1 to 3 is going to be equal to x 4 to 6. This should make sense, right? The derivative of x, y, z is, there's these three right here. And then finally we have the derivative of the next few terms. And this is going to be the force vector divided by the mass. We'll add in friction later. I think this video is already at like 40 minutes long. Yeah, I'll add it into the last 10 minutes, not now. All right, so yeah, now we've defined our equations of motion. Now we just have to go back all the way to the main file and edit this accordingly. So I'm just going to pull these numbers from the perspective of this video. These numbers came, out of thin air, but just trust me, they did not. They're values that I played around with a little. So yeah, our mass we're going to assume is going to be 50, and we're going to pretend like we're shooting something from from somewhere kind of near where I live, latitude, and this is going to be 45 degrees. So we've done that, and then we'll define our initial state vector as, say, I don't know, 0, 0, 0. Right, so we're assuming we're on the 45 degree latitude line. We're assuming we're nowhere, we haven't moved at all in relation to it. And then we have, these numbers look like they came out of thin air. They did not. I've tested it. Yeah, we don't need to define this anymore. Length of x, first variable is already in. We can get rid of this k and m here. Solver, we're not doing this, we're doing gravity EOM. And the inputs for gravity EOM are m and latitude. So let's do that. Let's change this to m and latitude. And this should be pretty good. I'll get rid of this for now, just because it's getting annoying now. All right. Then there's some other code. I'm not going to bother explaining how it came about. The Mathworks page does a lot better job of explaining it than I do. But basically, we're making a figure. It's going to have the name Cartesian position, and it's going to be in this position and this big. And there's going to be 3 plots within it. The first plot is going to be x position, which is how far east we went, and it's going to be plotting the x coordinate as it changes. The second one's going to be the y. Last one's going to be the z. The best way to learn this is by practicing. Anyway, let's see if we can run this only. Boom. Okay. So this is interesting. So first thing to notice, when we are shooting our projectile, we're shooting it straight up, right? Its initial position is 0, and its initial velocity is 400 in the up direction, 400 meters per second in the up direction. And so the z actually makes sense, right? It goes up, comes down, it's doing, normal parabolic quadratic, motion. But what's interesting is that the position also changes in the y and in the x and y direction. And as you can see, the x position changes as more or less a function of altitude, right? As we're higher, the slope is sharper, which implies that, the higher up we are, the more the x position will change. And the y is changing constantly, which is, it almost looks like it's accelerating. And the reason why this looks like it's accelerating is because the Earth is spinning underneath it. Wait, I messed up one of these. I messed up the explanation, but yeah. You can see that this one depends on the the height. This one is just constantly speeding up in one direction, and it's constantly moving north, right? Because that's the way we've defined our coordinate axes. And this kind of makes sense in that this is what happens when you shoot stuff. Whether or not this is actually what happens, I have no idea, but this makes sense, I think, in that if you shoot something too high up, the rotation of the Earth and the centrifugal force will throw it off balance, right? Because remember, we're shooting this thing straight up. Normally, we'd expect it to come right back down where we expect it to, but we can see that it's going to be off by like 54 meters in this direction and 45 meters in this direction. So yeah, things are changing. The other thing, okay, I'm not going to do it here because this video is way too long. It's 45 minutes long. But you can imagine if you wanted to add in, another force for friction, right? you would just, search up the equation for friction, figure out how to get it in, standard XYZ form, and then just add it to the end of this, and it would be accounted for. Uh, Further down the line, when we start doing like the rocket equation, I'll add that in, but for now I'm not going to. And so yeah, that's this tutorial. In the next one, we're going to look at getting rid of this one text file, or sorry, this one execute file. We're going to look into making, an actual, object vehicle, you could say, in MATLAB. And so yeah, that was this video. This is kind of long. If you find any mistakes, do correct me. I don't actually know if this is right. And yeah, that's all. All right, goodbye.